general form for the simple linear regression model is y equal to beta naught plus beta 1 x I, x I plus EI, okay? Alright, now, this is a simple linear regression model, okay? This is a simple linear regression model. Okay, so it is a simple linear regression model because it has just one explanatory variable explaining all the variations in y. Now, in this model, there are some things that are very important or what we should take note of. Here, on the left side of the equality, we have the response variable. This is usually the variable that we are trying to study changes in. Okay, for example, y could be consumption. Okay, so we're trying to use another variable, x, to explain what? Changes or variations in this variable y. Okay, so if we're able to do that, the purpose or the goal is usually to see if we can predict future values of y. That is actually what we use regression to do. Okay. Also in this model, you see that there are two parameters here, beta naught and beta 1. Beta naught is the intercept or the autonomous part of this model, which does not depend on what? Any explanatory variable. It's on its own. While beta 1 is the coefficient of this explanatory variable. Okay, so we can interpret beta 1 by how much the response variable y will change when there is a unit increase in what? In the explanatory variable. Okay, you can see it is multiplying it, right? Alright, so you see, because we are also aware that it is not possible for just one variable to explain all variations that will occur in y, because we believe there should be some other variables that should influence y, but we don't know them, or we assume that we don't know them. So what do? We include this epsilon, which is known as the stochastic error term. This stochastic error term is used to track the effect of all other variables that are not included in this model, which might cause what? Variations in y. For example, if y is my consumption and x is my income, this epsilon here, or the stochastic error term, will cover or we take care of other variables that could also influence my consumption, which is not represented in the what? In the model. So that is why it is called the stochastic error term. Now, you see, those variables are random. There are several other factors. There are random factors, okay, which we're not bringing in here. So, if we have this, we say we have a linear regression model. So another thing we need to understand is, why do we call it a linear regression model? Okay, I was explaining this the other time. It is called a linear regression model because it is linear in what? In parameters, and not in what? In variables. Okay, so linearity is actually tracked in terms of the parameter and not in variables. Okay, so this is why we call it a simple linear regression model, because we only have one explanatory variable explaining all the variations in what? In y. Okay, so but most of the time it is possible for us to have several explanatory variables, say k explanatory variables. These k explanatory variables, if we use it to formulate a linear regression model, it ceases to be a simple linear regression model. It becomes a multiple linear regression model. So we can specify a multiple linear regression model in this form. Okay, so we call this is a multiple linear regression model. Okay, so we call it a multiple linear regression model because we are having k explanatory variables explaining the variations in y. Even though we increase the number of explanatory variables that are explaining the variations in y, okay, we still believe that it's still not enough. So we still include our what? Our error term, which we still take care of what? Every other variables that are not included in the model. Okay, so this error term, like I explained before, is tracking all other variations that are outside the model. And it makes sense for us to do that. Okay? It makes sense for us to do that because in the real world, things are not as deterministic as it will be. So the error term makes the model non-deterministic to be what? Stochastic. Because this now takes care of random effects that may, induce variation in y. So this is a multiple linear regression model with k explanatory what? Variables. Okay. All right. Now this is just a very naive way of representing regression, or should I say, not really naive way, a non-compact way, okay, of representing regression model. So what we're going to do now is we're going to put the regression model in a compact form, in a matrix form, and I'm going to specify explicitly the various components of the matrix. So the multiple linear regression model in matrix form can be written in this form: y is equals to x beta plus e. Okay, now this is the matrix form of the simple linear regression model, and we're going to define what each of these elements stands for. Okay, what each of these parameters and variables in the model stands for. Now, y will be a vector of response: y1, y2, down to where? Yn. So y is a vector of response because now we're dealing with the matrices now, right? So y becomes a vector of response. Okay. Then x becomes a matrix of predictors. It's also called the design matrix. Okay, I like you to make note of that. X is a matrix of predictors, also called the design matrix. Okay, and this matrix is usually of full rank. Okay, I'm going to write the elements of this matrix now, and then we discuss why it is of full rank. Okay, so the matrix has this form. The first column of this matrix are all ones. Okay, and I'll tell you why it has ones. Then we have x1, 1, x1, 2, x1, 3, down to x1n. Okay, now the second column will be all observations of what? The first explanatory variables. Okay, now you see y has how many observations? It's usually n observations. When you want to carry out a regression analysis, you have a sample size, right, that you use. So that sample size is n. Y has n observations. X also has, the explanatory variables also has n observations. So in this first column, the first column would be, you see, this first index here means the first explanatory variable, x1. And this other one means the first observation of the first explanatory variable. Is that clear? So this here means the second observation of the first explanatory variable, down to where? The nth observation of the first explanatory variable. So here we're going to have x21, x22, x23, down to x2n. Okay, and we're going to continue till where? xk what? 1, xk2, sk3 down till xkn. Now, this is the matrix. And this matrix would be what? The matrix will have how many rows? The matrix will have, okay, it will have n, okay, n by what? K plus 1. That's the dimension of this matrix. So, the dimension of this matrix will be what? N by what? K plus 1. Okay, why is it n? Because the n is the number of observations per variable, right? Alright, then how many explanatory variables do we have? We have k explanatory variables, but then we also have to account for what? The intercept. This intercept is now, we track the contribution of this intercept by including what? This first column of what? Ones. So here we're going to be having 1, 2 to k, right? That is k columns, right? Okay, plus what? Plus 1. So that's why we have the dimension of this matrix is n by what? Is n by k plus 1. That is, it has n rows and k plus 1 what? Columns. So this matrix is called the design matrix, and it is of full rank. So a matrix is said to have a full rank, or the rank of a matrix. Okay. The rank of a matrix is the number of linearly independent row or linearly independent columns. Okay. Okay. Yeah, I said the rank of a matrix is the number of linearly independent rows or linearly independent columns of that matrix. That's when we say that is the definition of what? The rank of a matrix. The number of linearly independent rows or the number of linearly what? Independent columns. Okay. Now when we say a matrix is of full rank, if the matrix is symmetric, the rank of the matrix will be equal to what? Will be equal to n. For example, if a matrix is if this matrix is a symmetric matrix, of course it has to be, the number of rows will have to be equal to the number of columns, right? For example, if it is n by n, what will be the rank of the matrix? The rank of the matrix S will be equal to what? N. That is the number of rows or the number of what? Columns. So that is when we say the matrix has a full rank. Okay. Now this matrix always has a full rank. The rank of this matrix is of the matrix is of full rank. Now another thing we have is B. In this definition, B is a vector of what? The parameters that we want to what? Estimate. Okay, I'm coming. Let me just write this, then I'll take your question. So B contains beta naught, beta 1, beta 2, down to where? Down to beta k. Okay, down to beta k. Now it means, what will be the dimension of this matrix? This matrix will have a k plus 1 by 1 dimension. That is, you know how many rows here, right? There are k plus 1 by 1. Alright, so that is for the beta. Okay, then the last one is the error. The error term would have the same dimension as y. Okay, will have the same dimension as y. It will just be a vector of errors, e1, e2, down to where? Down to en. So this is basically the linear regression model in matrix form. Okay, now before I take your question, if you use this matrix, if you use this, if you use this to multiply this, you're going to get this equation back. Yes. Okay, I said if you use this vector to multiply this matrix, you will get this equation back. Okay, yeah, you're going to get this equation. So this is a more compact way of representing linear regression. Okay, it's very easy, and of course, as we're going to be finding proofs for some of the things that we need to find their proofs, you discover that working with the matrix approach is way easier than using the scalar representation of the model. Okay, so this is what we have. Quickly, let me take your question, please. You didn't get what? Full rank, yeah. I said, if this matrix is a symmetric matrix, or it's a matrix that the number of rows is equal to the number of columns, the rank of the matrix will be equal to the number of rows or the number of columns. Then we say the matrix has what? Full rank. Okay. So, yes.
In this case, this number of rows equal to number of columns.
Yeah, it's always the case sometimes. Well, in this case, the number of rows is not equal to the number of columns. Okay. If the number of rows is bigger, okay, now let me explain it to you. If the number of rows is bigger than the number of columns, the rank, for example, if the matrix is m by n, you know this is the number of rows, and m is less than or equal to n, the rank of that matrix X would be equal to what? N. If n is greater than or equal to n, the rank of that matrix X will be equal to what? Or equal to n. It's like the converse of what holds. So it is still a full rank, okay? Alright, the idea is this matrix is a matrix of full rank, and it has implication in in terms of a lot of operations that we do with the regression model. Okay, for example, if we want to do the decomposition of the matrix and so on and so forth, we'll need that. It's so important for us to go back or make recourse to the fact that this is a matrix of full rank. So this is the model. Okay. Yes.
Sorry, sir, I'm still not comfortable with the definition that the matrix is of full rank, the matrix is symmetric. So in this case, I will have
no, that's not what I said. I said if it is symmetric, the rank of the matrix would just be equal to the number of rows or the number of columns. Okay.
Okay, so what's the definition? When can we say a matrix is a full rank matrix?
Okay. Now, when it's a full rank matrix, if it's a full rank matrix if the rank of that matrix is equal to what? Is equal. Essentially, we can apply the concept of full rank to a square matrix. Really, okay? You know, a square matrix is the matrix that the number of rows is equal to the number of columns. So, when the rank of the matrix is equal to the number of rows, which is in turn is equal to the number of columns, it's of full rank. Are you getting it now? Because as we operate on this matrix, you're going to see, you discover that yes, the design matrix it's always of full rank anyway. Okay, but here, like I provided here, the rank of the matrix, okay, if the number of rows is less than or equal to the number of columns, then the rank of the matrix is essentially equal to the what? The number of columns, and then vice versa. Okay, but what I want you guys to just take note of in this discussion is the fact that this matrix is of what? Is of full rank. Okay, so what we're going to do now, having specified the model, what we're going to do now is to examine the assumption of the linear regression model before we can go into the estimation, because it is the assumption that will drive how we're going to find this estimate. Okay, so let's see the assumptions of the linear regression model. Okay, the first assumption we make concerning the regression model, most of the assumptions we make about the linear regression model are made with respect to the error term or the stochastic error term. So the first thing is we assume that the mean of the error term, the expected value of the error term is 0. That is, the expectation of E is equal to 0. Please, E is a vector here, right? E is a vector. Please listen now. If E is a vector, it means this supposed 0 is not the ordinary 0. It means it's a what? A 0 vector. Okay? Now we're going to be dealing with matrices in higher dimensional space. We're not dealing with scalars now. So that is the first thing. Okay. The second assumption we make is that the error term has equal variance. Okay? the variances of the error is what? Is equal. So we can write it in this form. The expected value of E transpose E also equal to the expected value of E is equal to sigma squared. Constant variance. And of course, we always put this the identity matrix. Okay, because we're dealing with matrices now. Okay, now I can't just write sigma squared. Okay, you know why I can't write sigma squared? Because it's not a scalar. However, it's like multiplying. The identity matrix is the same as, it's like 1 in scalar algebra. So it's like multiplying it with 1. It doesn't change. Now, if you use, you know what this is going to give to you? If you multiply a constant with an identity matrix, you're going to have a matrix of columns and 0 everywhere, right? Everywhere else. So that's why we always put the identity matrix. Okay, so this is how to get variance. You know, generally, I'll quickly write this. If you want to find the variance, okay, let me quickly give you guys why we write it in this form. Okay, why we write it in this form. If you need to define variance of a random variable, this is how you define it. The variance of a random variable x, okay, is always equal to the expected value of x minus the expected value of x. Okay, the expected value of x minus the expected value of x all squared. This is how you define variance. Okay, all right. Okay, this is how you define variance. Variance is the second moment of a random variable around the mean or about the mean. Okay, variance is the second moment of a random variable about the mean. So this is the definition. Now, if we are to bring this in context, like if we want to define variance for the error, how do we do it? If we want to define the variance for the error, we're supposed to do variance of E. Now, you see, this is not a matrix, it's just one variable, right? Oh, yes. It's the second moment of a random variable about the mean. Okay. The second moment of a random variable about the mean. Alright. Now, if we need to find the variance of E, okay, E is a vector. It's not just one single random variable, right? So how do we define it? It is going to be the expected value of E minus the expected value of E times E minus the expected value of E transpose. Now, I remember telling us yesterday that when we transpose, when you multiply a matrix or a vector and it's transposed, what are you doing? You're trying to create squares, right? Okay, that's what I said, right? So to take care of this square, we brought in the transpose, right? Okay. Now, check it out. We're dealing with the variance now, the variance of E. I'm just trying to explain why we specify it in this way. In the first assumption, we already know that this is what? Is 0, right? So what becomes the variance? This is expectation of what? Of E. Here is also 0, right? So what are we going to just have? E transpose. Okay, let me be E prime. So that is why we write it in this form. Okay? You see the reason why we write it in that form. And we say it's equal to sigma squared. So that's what it means by constant variance. The variances of the error is what? Is constant. Okay, now this is a very, very important assumption we've made. Okay, and this assumption is known as what? Homoscedasticity. Homoscedasticity. The assumption of homoscedasticity. Homo means same. Skedastic means spread. That is the same spread. Yeah, the same. Okay. All right. So, is it clear? Yes. Okay.
The reason why he equated to variance spread at the end,
Here.
the last line,
Okay.
is because he squared the expectation of, right?
No. You see, this is the symbol for variance. We're just trying to, variance is always sigma squared. Okay, I mean, this is just notational. It could be any value, right? It could be any value, but we're just putting it here. And then we need to attach it to the identity matrix to tell us that, yes, we're not really on the lower space, but on the high dimensional space of the matrix. Okay, so that's how we arrive at this. So it's homoskedastic. If the variance is not constant, so what do we call that? Heteroskedastic. That is why in regression theory, heteroskedasticity is a problem that we must contend with. The reason is this: if these assumptions we're making now are not satisfied, the OLS method that we're going to establish as we move on, it's going to be difficult for us to, they're going to produce very disturbing estimates. Okay, so that's it. Now, another assumption we make is that there is no autocorrelation among the error. There is no autocorrelation among the errors. That is, one error is never related to what? Another error. So, this assumption is the assumption of what? No autocorrelation. So, just like the problem of heteroskedasticity, the problem of autocorrelation has serious consequence for our what? For our regression model. If you're applying regression in your research, you have to be sure, you have to check that these problems are not present. Else, the results you will be giving out, the recommendations you will be giving out will be very wrong. Okay? It will be very wrong. So that is why these assumptions are so important. Then another assumption we make is that in that case, we can just put everything together and say that the error is normally distributed with zero mean and what? A constant variance. How did we arrive at that? We already know that the mean of the error is what? 0. And then we've already found out that the variance of the error is what? Sigma squared times the identity matrix. So the error is normally distributed with 0 mean and what? The constant variance. Okay. The number 3 is the assumption of no autocorrelation. Okay. And it's telling us that the errors, none of the errors should be related in any way. That's why you see that we need to put 0 here. The covariance is equal to 0. The covariance between the errors should be 0 for I not equal to j. Okay. This is no autocorrelation. Okay. If it is not equal to 0, whether it is negative or positive, there is a problem. If the correlation between any two errors is not equal to 0, what do you have? You have what is called what? Autocorrelation. Okay? You have autocorrelation, and it's a serious problem in regression, like I said before. And then number 4 is that the errors are normally distributed with 0 mean and a constant variance. Okay, now that we've established that, number 5, we also believe that y is also normally distributed. Y is also normally distributed. Okay, y is also normally distributed. Okay, there is a distribution for y. Y is normally distributed, and we also make this assumption that there is no multicollinearity. Okay, there is no multicollinearity. No multicollinearity. Now, what does multicollinearity means? Multicollinearity means that the explanatory variables, that is the x in the model, none of them are what? Related, okay? Or they should not have a perfect relationship. If they do, it will be a serious problem. If they are related, what is the implication? It means that it's like one explanatory variable is already doing the prediction, and then there's something that is related to it. When we are finding the OLS estimate, we discover that we cannot really invert that particular matrix, that inverted matrix that we're going to see as we move on. So, no multicollinearity is a serious problem in regression research we carry out with regression. It is a situation, multicollinearity is a situation where the explanatory variables are what? Correlated. Okay, a severe case is when they are what? Perfectly correlated. In that instance, you're going to have a singular matrix during the estimation process, and everything is just going to blow up. Okay, so there should be no multicollinearity. Now, there could be some other assumptions that you have as regards the regression model, but these ones are the key assumptions we make when we are carrying out regression. Yes?
That's a lot.
Yes.
So can we start the application?
No. We are here to prove this.
Everything.
Yes.
No application.
We did applications yesterday.
I think you are repeating yesterday's class.
Oh, really? Yes, that's what I'm doing actually. But we're not done with the establishing we're not done establishing. Okay. Alright, so let's go on please. We have made the assumption. The next thing is to carry out the estimation. Okay, so let's go to estimation. The focus is usually to find the estimate of B. We need to find the estimate of B because if we know the value of B, we will be able to predict Y for any given value of what? Of X. So, and we are told that the OLS estimators, that is the ordinary least square estimator, is the best, and that was emphasized by the Kuzmakov theorem. So, the ordinary least square estimator. Ordinary least square estimator. Okay. The ordinary least square estimator, which is the OLS estimator, is the best linear and unbiased estimator of the regression model. So, this is where the blue property comes. Best linear unbiased estimator. And that was emphasized by the Kuzmakov theorem. We're going to prove the Kuzmakov theorem before we leave. Okay? We're going to prove the Kuzmakov theorem. Now, alright, so we have it. The best linear unbiased estimator is the OLS estimator or the ordinary least square estimator of these parameters. So how do we find the OLS estimator? That is what we need to consider. The OLS estimator is obtained by minimizing the sum of squares of the error. The OLS estimator is obtained, the OLS estimator of the regression parameter B is obtained by minimizing the sum of square error. Okay, that is how we obtain the OLS estimator. So let's see how we do that. Let's find the estimation. Given this regression model, x equals y equals x beta plus e, our error is the same as x. Okay, by minimizing the sum of squares of the error. By minimizing the sum of squares of the error. Okay, that is how we obtain the OLS estimator. You're welcome. Okay, it makes sense for us to write this, right? All we did was to make the error term the subject of the formula, right? Now, if we write it in this form, this would also make sense. Y minus x beta transpose y minus x beta. This also makes sense, right? Now, we are now transposing E. if we are transposing E, it means we are transposing this particular what it is equal to, right? And then this is another E. Because I just stated, a while ago, that when we are dealing with vectors, for us to square the component of the vectors, what do? We take the transpose and multiply the matrix together. That is why it's like this. Okay, so this is how we're writing. Does anybody have a query? This is very clear. Okay, so now that we have arrived here, this is the same as y transpose minus b transpose x transpose y minus x beta. The rule of transposition, we brought it in here. When you are transposing this matrix, what happens? You transpose them individually. You transpose y. But when you are transposing these two, because they are, they're multiplying themselves, what happens? The b transpose is written first before the what? The x transpose. So please, I like to make note of that. That is very important. Okay. Yeah, what I'm trying to say is, you want to transpose this entire matrix. You transpose it, component wise. You transpose y, but x and b are both what? They're multiplying each other, right? So what do you do to transpose them? You transpose the b is written first, the b transpose is written first before the x transpose. Please never lose track of that. But the truth is, it's still the same matrix anyway. It's the same. Alright. So we have this. So what do? We just make recurse to algebra and expand this bracket. Okay, so let's expand the bracket. When we expand the bracket, we're gonna get y transpose y minus y transpose x beta minus beta transpose x transpose y plus beta transpose x transpose x beta. Okay, we just open the brackets. Use the normal algebraic process of using this is like factorization, right? And use this to multiply everything here. Use this to also multiply, and then you arrive at this. So we can also verify that these two matrices are the same. They are the same. Okay? These two matrices are the same. So we just need to write one of them. Since they are the same, this gives us y transpose y minus 2 beta transpose x y plus b x prime x transpose x of beta. So hello, these two matrices are the same, please. They are the same. This is y transpose x beta, and this is beta transpose x transpose y. It's the same. You see, in this case, in this instance, y is transposed. Here, it is not transposed, right? Here, x and beta are not transposed, but it is transposed here. If you rearrange, it's going to give you the same thing. Okay? Yeah, the last one is, we have to write it again. Okay, beta transpose. Thank you. We have beta transpose. Okay? Yes, it's the same. That's why, it's like saying 4 minus A plus 6, for example. This is going to give us 4 minus 2A. Is that correct? Right? Plus 6. So we're just trying to have that. So we arrive at that. Very clear. Okay. So remember, this is still the sum of squares error. So what do? I said to obtain the OLS estimate, we try to minimize, right? And we all know that minimization is actually what we do with calculus, right? We find the first derivative of the function and equate to 0. Solve for the stationary point for us to minimize or maximize the function, or whenever we're optimizing, as it were. So we're going to differentiate this equation. So with respect to what? With respect to b, because b is the argument, right? Is what we want to find the estimator for. We're looking for the estimator for b. So this gives us the e prime e, the b, this there is no b in this component, right? It becomes what? It becomes 0, right? Okay, here there is b. It becomes 2x prime y, because if you differentiate 2, it's like saying 2. Yeah, if you differentiate with respect to b, the b will go away, right? So we're going to be having minus 2x prime y. Please, at this point, whether it is b prime or b, it's still the same, right? It's the same component. Everything is just that when you transpose, you're going to be having either a vector or a row vector or a row or a column vector. It doesn't change anything. Okay. All right. So plus here, this is b transpose b. It's like a square, right? Because, I mean, anytime you're transposing, this is not a problem because the values are what? They are fixed. So, what are we going to have here? This becomes 2b x transpose x. It's like saying b squared x prime of x. And we are differentiating. Okay, but it's a sin for us to write it as b squared. Why? Because this is matrix, right? Okay, so it's going to come in that form. So, and when you are done differentiating, what do you normally do when you are optimizing? You equate to what? To 0. Okay, equate to 0. Great. Yes. Okay, what I said is with respect to this b, right? Okay, this differentiation. When you differentiate this, it does not have any term. You know when you differentiate with respect to b, right? There is no b here, this goes to 0, right? Now there is b here. If you differentiate with respect to b, what happens? You'll be left with negative 2x prime y because b is going to go away. Here is beta prime, is b transpose. This is a constant, it's not a problem. Okay, anytime you are having transpose multiplying a matrix that is transposed multiplying itself, it's like squaring the matrix, so it's like 2 squared. And you know when you have when you're differentiating x squared, what are you going to have? It's 2x, right? That is how we obtain 2bx transpose x. Okay. And then we equate to 0, right? Okay. Now that we've equated to 0, you discover that minus 2 beta x prime. Oops. Okay, let's leave. Okay, now this is going to give us beta x prime x equal to 2 x prime y, right? 2 is on both sides of the equality, it can go away, right? Okay, so we left with what? B x prime x equals x prime y. So how do we make b to stand alone? To make b to stand alone, we need to find the inverse of the matrix, right? We need to multiply both sides by the inverse of what? This matrix. So we're going to be having b x transpose x inverse x transpose x equal to x prime y x prime x inverse x prime y. So check out what we did. I just multiplied both sides by what? The inverse of this matrix. Okay? That's what I did. I've not changed anything. You know, in algebra, if you do something to the right hand side and do the same thing to the left hand side, it leaves the equation unchanged, right? So it's not a problem. So what I did was to multiply both sides by the inverse of this matrix. So, you know, when you multiply a matrix multiplied by its inverse, what is it going to give to you? It will give you the identity matrix. So we're going to be left with what? K plus 1 in this instance, b equal to what? X prime x inverse x prime y. Of course, you can do away with the I. It's not a problem. So this becomes the OLS estimate of the regression model. This becomes the OLS estimate of the regression model. So that is how we arrive at the OLS estimate. So we've been able to find the estimate. Okay. Yes. Yeah. We just multiply both sides. We're trying to ensure that B stands alone. You understand? It's like saying 2x is equal to 4, for example. Okay, I want to make x the subject of the formula, x will stand alone. I can say multiply both sides by the inverse of 2. That makes sense, right? That means 2 times 2 squared x equals 4 times what? Sorry, 2 inverse. Is that correct? So what will this give to me? 2 times, you know, this is same as 1 over 2. Right? Of course, this is going to go. And then x will be left alone in peace. And then we're going to have the other side will be. That's what we did. We're just trying to mimic what we do in algebra, in scalar algebra, in higher dimensional space involving matrices. So, this is what we have. Now, we have obtained the OLS estimate, and I'm happy you guys have been able to grasp the concept very well. Okay, it's not everything that you cram. Okay, you should know it. Yeah, you should be able to know this. Okay, yeah, because in your other courses, nobody is going to. You're supposed to be taught this in statistics, in statistical method. That's why we're teaching it. Because other lecturers are going to assume we must have what learned it. Yeah. And when they are applying it and you don't understand the meaning of how this thing works, it's just going to be, it will seem as though you are doing something abstractive. Okay, so we have obtained the OLS estimate. What's the next thing we need to do? We need to find the mean and the variance of this estimate. Remember the Guzman theorem. The Guzman theorem states that the OLS estimate of this regression model is the best linear unbiased estimator in the class of all linear unbiased estimators, because this estimator has what? The minimum variance. That is the smallest variance. In other words, it's very efficient. That's what the Guzman theorem tells us, right? So we need to, for us to even prove the Guzman theorem, we need to find the variance and see the structure of that variance to really verify whether or not the Guzman is really the minimum variance or not. So that is the reason why we're going to find the mean and the variance of this estimator. So that's what we're going to do. Okay, we're going to come to this side of the board. This was here originally, right? This is here originally. So what I did was I inverted the matrix and used it to multiply the left-hand side. And also, yeah. So when you multiply this, it's going to cancel out itself. This is going to leave B alone. We want B to stand alone.